What is an agent? An AI agent is an AI model that has agency. It has the ability to take action and interact with an environment in pursuit of goals. This represents an evolution beyond simply generating text. If we look at the abstract definition of an agent as it has been used in computer science in the past, it is something that can take actions, sense its environment, operate within its environment, have a memory, and plan. In the early days, around 1960, the term agent was used within AI to describe components that executed specific tasks autonomously. Over time, the definition evolved to encompass a broader range of functionalities, including reasoning and learning from interactions with their environment. By the 1990s, the concept of agents had matured significantly, leading to discussions about their roles in networked systems and their ability to collaborate with other agents to achieve shared goals. The term has been around for a while in the world of computer science, but it's quickly gaining awareness in the business world. Agents are on the rise because LLMs serve as powerful building blocks for agents, providing the core capabilities of language understanding and reasoning. However, an agent transcends the limitations of a standalone LLM by incorporating the ability to interact with an environment, take action, and pursue goals. This often involves integrating the LLM with other systems, such as planning algorithms, memory modules, and various tools for external interaction. Examples of agentic systems include advanced chatbots that remember past interactions, research assistants that can synthesize information from web sources, coding assistants that generate and debug code, and game-playing agents that utilize LLMs for strategic decision-making. An LLM-empowered agent represents a significant advancement towards more autonomous and interactive systems, leveraging the power of language models to perceive, reason, act, and ultimately achieve defined objectives within a given environment. Is an LLM by itself an agent? No. A key distinction between a chatbot, similar to the first version of ChatGPT, and an agentic chatbot is the ability to perform tasks. The only task that GPT 3.5 performed was to return text back to the user. Consider the following example involving RAG. If you instruct an LLM, add this conversation to my shared business meetings. The agent could then fire off a process that saves the conversation to store it, so it is retrievable by the user and the user's team. Each member of the team could explicitly add to the RAG knowledge base conversationally, making it more convenient than database entry. The ability to fire off an action based on the user's intent is the added functionality that makes the system an agentic one. Andrew Ng, an AI Stanford adjunct professor and leading AI thought leader, says agentic AI is the most important AI technology to pay attention to right now. Andrew outlines 4 major design patterns that are foundational to agentic reasoning in AI: reflection, tool use, planning, and multi-agent collaboration. These patterns enable AI agents to move beyond simple input-output tasks and engage in more complex, iterative processes that resemble human thought. Let's walk through each of them. Tool use empowers a language model to not just process and generate text, but also to trigger specific actions, as we discussed before. This is accomplished by prompting the model in such a way that it recognizes when an action is needed and generates the appropriate request or command to initiate that action. For example, instead of simply answering a question about the weather, a language model equipped with tool use could be prompted to access a weather API, retrieve the relevant data, and then present it to the user. The model transitions from merely understanding and responding to a request in text to also instigating action in a separate system to gather further information. The range of tools a language model can interact with is vast and continuously expanding. It can involve anything from making API calls to various online services like search engines, databases, or productivity tools, to executing code in different programming languages, to even interacting with physical devices through specialized interfaces. Imagine a language model that can not only find recipes online, but also automatically add the ingredients to a user's shopping list, or even preheat the oven through a connected smart home system. This ability to interface with a variety of external tools allows the model to tap into a wealth of information and functionalities that far exceed its inherent capabilities. Ultimately, tool use transforms the large language model into a much more dynamic and versatile agent. It becomes a true doer, capable of taking initiative, gathering information, and performing tasks that would otherwise require manual intervention. This opens up exciting possibilities for automation, enhanced user experiences, and the development of sophisticated AI-powered applications that can seamlessly integrate with the digital and physical world around them. In a sense, tool use provides the bridge that allows the cognitive abilities of the model to be applied to the concrete needs of the real world. Reflection. The reflection design pattern represents a significant advancement in the development of self-improving artificial intelligence. It is essentially a process wherein an AI agent engages in a cycle of self-critique and refinement, mirroring the metacognitive practices often employed by human experts. At its core, this pattern hinges on the AI's ability to evaluate its own output objectively, identify areas for improvement, and then utilize these insights to enhance its subsequent performance. This is conceptually similar to a seasoned software developer who, after writing a block of code, meticulously reviews it for potential bugs, logic flaws, or areas where efficiency could be improved before integrating it into a larger system. The implementation of the reflection pattern often involves a structured approach where the AI first generates an initial output, such as a piece of text, a code snippet, or a proposed solution to a problem. Following this, the AI is prompted to take on a different role, that of a critic. In this critical role, the AI examines its own output, applying a set of predefined criteria or learned standards to assess its quality, accuracy, and effectiveness. It scrutinizes for errors, inconsistencies, or any deviations from the desired outcome. This self-assessment generates valuable feedback, essentially highlighting specific areas that require attention or modification. Armed with this self-generated critique, the AI then transitions back into the role of the creator. However, it is now informed by the insights it gained during its critical review. It proceeds to revise its initial output, addressing the identified shortcomings and striving to improve upon the previous iteration. This revised output becomes the new baseline for another round of self-critique. This iterative process of generation, reflection, and refinement can be repeated multiple times, with each cycle theoretically leading to a more sophisticated and improved output. The ultimate goal is to leverage this cyclical process to guide the AI toward producing more robust, reliable, and high-quality results. The reflective pattern also aids in reducing common issues such as factual inaccuracies, logical inconsistencies, or undesirable biases in its output. The power of the reflection pattern lies in its ability to enable AI to learn from its own mistakes and progressively enhance its performance, without requiring constant external supervision or explicit feedback. This autonomy and self-improvement is crucial for developing AI systems that are not only capable of producing high-quality outputs, but also of adapting and evolving. By mimicking the introspective learning process that humans naturally employ, the reflection pattern provides a pathway toward creating more intelligent and self-sufficient AI agents capable of handling complex tasks with increasing reliability and generalizing their knowledge to novel situations. The result is AI more adept at problem-solving and capable of generating outputs that are more aligned with human expectations and standards. Let's illustrate the reflection pattern with an example of an AI tasked with writing a short story about a detective solving a mysterious theft. In its initial attempt, the AI generates a story where Detective Harding finds a stolen necklace hidden in a villain's apartment. The story is fairly basic, lacking detailed descriptions and with a plot that unfolds too predictably. The villain, Mr. Smith, is captured easily without much resistance, and the story concludes abruptly. This first draft serves as the baseline for the AI to begin its reflective process. Transitioning into its critical role, the AI analyzes its own work. It identifies several weaknesses. For instance, the AI might critique, "The narrative lacks suspense. Detective Harding solves the case too quickly, without encountering significant obstacles. The character of Mr. Smith is underdeveloped, acting more as a placeholder than a compelling antagonist. The setting is vaguely described, failing to immerse the reader in the scene. Furthermore, the story lacks a meaningful theme or message." This self-generated critique highlights the areas that need improvement, setting the stage for the revision phase. Informed by its own critique, the AI revises the story. In this iteration, Detective Harding now faces a series of misleading clues and red herrings. The AI introduces a rival detective who initially suspects Harding himself, adding conflict and tension. Mr. Smith is now a more cunning character with a plausible backstory, making his motives and actions more complex. The AI enriches the story with vivid descriptions of the city's shadowy alleys and the detective's cluttered office, enhancing the atmosphere. It also weaves in a theme about the nature of trust and suspicion. This revised story is more engaging and sophisticated than the first draft. The AI, however, doesn't stop there. It once again assumes the role of the critic, evaluating the revised story. It might observe, while the plot is more complex and the characters are more developed, the pacing feels uneven. Some scenes are rushed, while others drag. The theme of trust is present but could be explored more deeply. Additionally, the dialogue at times feels stilted and unnatural. This critique will be addressed by the AI in its next revision of the story. For example, the AI might add more dialogue and improve the pacing of the story in its next draft. This would result in another self-critique, which would lead to another round of refinement. This iterative cycle of generation, reflection, and refinement continues. Each iteration builds upon the last, incorporating the insights gleaned from the AI's self-critique. Through this process, the AI gradually hones its storytelling abilities, learning to craft more compelling narratives, develop more believable characters, and construct more immersive worlds. The final output, after multiple rounds of this reflective process, will be a significantly improved short story that demonstrates a higher level of coherence and quality compared to the initial draft. Planning. Planning is a fundamental cognitive capability that enables AI agents to move beyond simple, reactive actions and engage in complex, goal-directed behavior. By enabling them to break down intricate tasks, anticipate future needs, and strategically sequence their actions, the planning pattern empowers AI agents to address challenges that require more than just immediate, one-off solutions. It is a crucial step towards creating AI that can truly understand and interact with the complex world around them, demonstrating a level of strategic thinking that is fundamental to solving multifaceted, real-world problems. Let's shift our focus to a LLM agent and illustrate the concept of planning in that context. Consider an LLM agent whose goal is to write a comprehensive research report on the impact of AI on the job market. This is a complex task that requires the LLM to go beyond simply generating text based on a prompt. It necessitates a structured and well-thought-out approach, embodying the essence of planning. Initially, the LLM agent needs to analyze the task and decompose it into its constituent components. It needs to understand that writing a comprehensive research report involves subtasks such as conducting research, gathering data from various sources, analyzing trends, forming arguments, outlining the report, drafting different sections, citing sources, editing, and proofreading. It's about building an internal representation of the task, understanding the different aspects of the research topic, e.g., types of jobs affected, geographical variations, long-term versus short-term impacts, potential for new job creation, and identifying the necessary resources for information gathering. The LLM needs to determine the scope and depth of the report, forming a clear picture of the desired end product and a strategic path to achieve its goal. Next, the LLM agent needs to establish dependencies between these subtasks and sequence them logically. For example, it understands that it can't write the analysis section before conducting research and gathering data. It knows that outlining the report should precede drafting individual sections, and that identifying relevant keywords and search terms will enable the process of conducting research effectively. It recognizes that it needs to analyze the data to identify trends before forming arguments about the impact of AI on the job market. The agent also understands that a specific section on policy recommendations might be made after a section analyzing data. Similarly, it recognizes the need to cite sources correctly and understands that this requires keeping track of the sources consulted during the research phase. This sequencing creates a coherent workflow, ensuring that each step logically follows the previous one and contributes to the overall objective of producing a well-structured and informative research report. As the LLM agent executes its plan, it continuously monitors progress and adapts. For instance, during the research phase, it might discover that there's a wealth of information on the impact of AI on automation in manufacturing, but limited data on its impact on creative industries. This discovery might prompt the agent to adjust the scope of the research, perhaps focusing more on the well-documented areas, or expanding the research to include expert opinions or case studies to fill the gap. Similarly, if it encounters conflicting data points during the analysis phase, it might need to revisit the research phase to find additional sources, or refine its search criteria to reconcile the discrepancies. It could also realize that certain sections are intertwined and combine them. For example, it could find that combining types of jobs affected and potential for new job creation produces a better, researched, and more helpful output. The LLM agent might also discover that a particular section is becoming too lengthy or unwieldy, opting to divide it into smaller, more focused subsections. This dynamic adjustment ensures the report stays focused, relevant, and of high quality. Through this example, we see how an LLM agent leverages planning to tackle the complex task of writing a research report. By breaking down the task, establishing dependencies, sequencing subtasks, and adapting to new information encountered during the process, the LLM agent demonstrates a higher level of cognitive ability than simply responding to prompts. It showcases the ability to work strategically towards a complex goal, mirroring the way humans approach similar intellectual endeavors. This planning capability is what elevates LLMs from being sophisticated text generators to becoming true AI agents capable of independent research, analysis, and the creation of original, insightful content, all necessary to solve real-world problems. Multi-agent collaboration. Finally, multi-agent collaboration leverages the concept of having a single large language model play multiple roles, or agents, that interact with each other to solve a task. Each agent can specialize in a particular aspect of the problem, such as coding, critiquing, or planning. By prompting the AI to switch between these roles, developers can simulate a team environment where different agents contribute their expertise. This approach has been shown to significantly improve performance on various tasks, likely because it mirrors the collaborative nature of human problem-solving, where diverse perspectives often lead to better outcomes. This pattern is a powerful tool for creating more sophisticated and capable AI systems. Multi-agent collaboration is especially powerful when it comes to coding. Andrew Ng presented compelling evidence of multi-agent systems over single large language models, LLMs, in certain tasks. He highlighted that while single LLMs excel at zero-shot prompting, where they generate text from start to finish in one go, they fall short when faced with complex tasks requiring iterative refinement. Multi-agent systems, in contrast, can employ an iterative workflow akin to human thinking, involving planning, drafting, critiquing, and revising. This iterative process allows multi-agent systems to achieve significantly better results on coding benchmarks such as Human Eval. Human Eval is a benchmark developed by OpenAI to evaluate the code generation capabilities of LLMs. It presents models with coding puzzles and measures their accuracy in solving them. A multi-agent system using GPT 3.5 outperformed the much more advanced GPT-4 model operating in a single-agent, zero-shot manner. Specifically, the GPT 3.5 multi-agent system achieved around a 95% success rate on Human Eval, dwarfing GPT 3.5's 48% and even GPT-4's 67% success rates in their standard configurations. This stark difference underscores the power of agentic workflows in enhancing the performance of LLMs. Even with an inferior model, the right multi-agent architecture can beat the better model. Creating an agent. To set up an agent, it is essential to understand the components involved, how tools are defined and triggered, and the frameworks available for implementation. This process can be broken down into several key steps. Defining the tools. The first step in setting up an LLM agent is defining the tools that the agent will use. Tools can range from simple functions to complex integrations with external APIs and databases. Common tools include web browsing capabilities, mathematical computation tools, and document summarization features. For instance, platforms like Anything LLM allow users to select from default skills such as scrape websites or summarize documents, which are enabled by default and cannot be disabled. Additionally, developers can create custom tools tailored to specific tasks using frameworks like LangChain, which provides a variety of pre-built tools for different applications. Triggering mechanisms. Once the tools are defined, it is crucial to establish how they will be triggered during the agent's operation. Typically, triggers are based on user requests or specific conditions outlined in the agent's configuration. For example, when a user poses a question that requires web browsing, the agent can automatically invoke the web search tool. This process involves setting up a control logic that determines when and how each tool is activated based on the context of the interaction. The prompts given to the LLM also play a significant role in this process. They guide the agent on which tools to use and how to respond appropriately. The tools for creating agents are ever evolving. At the time of this writing, Google, Anthropic, and OpenAI all have LLM models that support tool use. The next step in building an agent is deciding the modality of the agent. The modality of an AI agent refers to the way it interacts with the world. Specifically, the types of input it can process and the types of output it can generate. Traditionally, AI agents have often been confined to a single modality, like text or voice. Text agents, like the large language models we've discussed, excel at processing and generating text. They can engage in sophisticated text-based conversations, write different kinds of creative content, translate languages, and answer your questions in an informative way, even if they are open-ended, challenging, or strange. Text-based agents are powerful because they can be deployed in many places, including SMS messages, WhatsApp, Messenger, Instagram, and your own custom app. Voice agents. Voice agents have received well-deserved attention in the last year. Unlike the poor quality and high latency interactions of the past, today's voice agents are capable of conducting real-time conversations with a visceral-sounding voice. For businesses and entrepreneurs, voice agents offer immense potential to improve customer service and operational efficiency. For instance, they can handle customer inquiries 24/7, reducing the need for human intervention while maintaining high-quality interactions. A voice agent in an e-commerce business could assist customers by answering product-related questions, tracking orders, or providing personalized recommendations based on user preferences. Similarly, in industries like healthcare or finance, voice agents can be deployed to schedule appointments, provide account information securely, or deliver reminders all through simple voice commands. Businesses can customize voice agents to reflect their brand's tone and personality, ensuring consistency in communication across all customer touchpoints. Additionally, these agentic systems can be trained on industry-specific data to enhance their domain expertise. For example, a legal tech startup could deploy a voice agent trained on legal terminology data to assist clients with basic legal queries or document preparation. Let's dive into how companies are using voice agents. In the automotive industry, SoundHound AI has introduced an in-vehicle voice commerce platform, allowing drivers and passengers to order food directly from their car's infotainment system. This integration not only offers convenience, but also provides economic incentives for car manufacturers, as they receive payments for generating leads. Brands like Hyundai and Kia have shown support for this service. Amazon is undertaking a significant upgrade to its Alexa voice assistant. This initiative is set to introduce features such as Smart Briefing, which provides personalized daily news summaries generated by AI. The enhanced Alexa is designed to offer more natural conversations and intuitive smart home control, understanding casual phrases and discerning context and intent. To achieve these advancements, Amazon is exploring partnerships with companies like Uber and Ticketmaster, enabling Alexa to complete entire tasks independently by integrating directly with these services. Additionally, Amazon plans to launch a premium version of Alexa, utilizing AI technology from startup Anthropic, offering advanced features like complex query responses and personalized assistance. In December 2024, OpenAI introduced a new service allowing users to interact with ChatGPT via phone calls and WhatsApp messages. By dialing 1-800-ChatGPT, 1-800-242-8478, users in the United States can engage in voice conversations with ChatGPT for up to 15 minutes per month at no cost. These examples illustrate the expanding role of voice assistants in various sectors, showcasing their potential to transform interactions and improve efficiency in everyday tasks. Understanding multimodal agents. Multimodal agents represent a significant advancement in artificial intelligence, designed to process and integrate multiple types of data simultaneously. They are based on MLLMs, multimodal large language models. Multimodal large language models are AI systems that extend beyond traditional text-only LLMs by incorporating the ability to understand and process text, images, audio, and video. Unlike traditional LLMs that only process text tokens, these models are trained on diverse datasets that include multiple modalities, allowing them to understand the relationships between different types of information. For example, GPT-4o, formerly GPT-4 Vision, can analyze images alongside text, enabling it to answer questions about visual content, describe scenes, and understand complex visual textual relationships. There are different approaches to achieving multimodality. Some models, known as unified models, like GPT-4o, integrate multiple modalities directly into the neural network architecture during pre-training, allowing for seamless fusion of different data types within a single model. Examples include architectures like GPT-4o, which processes text, audio, and images in a unified manner. However, other approaches involve using external modules or adapters added to an existing LLM to handle different modalities. This might involve separate encoders or decoders for each modality, with their outputs then integrated into the main LLM. While this method uses multiple components connected together rather than a single neural network for all processing steps, it still leverages the core LLM as the central reasoning engine. Therefore, while some models process everything within one complex neural network structure, others use combinations of networks and tools to achieve multimodality. Applications across industries. The versatility of multimodal agents opens up numerous applications across various sectors. In healthcare, for example, these agents can analyze patient records alongside medical imaging data to provide more accurate diagnoses and treatment recommendations. In retail, they enhance customer service by interpreting visual cues from customers while processing their spoken inquiries, thereby creating a more engaging shopping experience. Google's Gemini 2.0, released in late 2024, showcases what multimodal agentic AI are capable of. For instance, the Gen Explainer demo allows users to select any topic and receive explanations in diverse styles via real-time conversation, utilizing text, audio, and video inputs. Additionally, Gemini 2.0 has been integrated into AI-powered smart glasses, enabling features like real-time translations, object recognition, and contextual awareness, enhancing user interactions in augmented reality environments. Multimodal AI agents are the future because they mirror the way humans naturally perceive and interact with the world. Just as we simultaneously process visual, auditory, and contextual information to understand our environment, these agents are breaking free from the limitations of single-mode interaction to create more intuitive and powerful experiences. Their ability to understand and respond across multiple sensory channels will revolutionize industries by solving complex problems that single-mode AI simply cannot address. AI agents are a leap beyond traditional LLMs, possessing the agency to interact with their environment, pursue goals, and learn through reflection. Frameworks and tools are emerging to facilitate agent creation, empowering developers and businesses to build increasingly capable systems. As generative AI continues to advance, the development and deployment of AI agents will reshape our interactions with technology, mirroring, and even exceeding human cognitive capabilities.